Alright, so I'm going to start this video on capacitors and inductors, and a brief little lesson on what all that is this. First we'll go over the symbols of what inductors are. This is an inductor. This is how they're drawn. Sometimes they can be drawn as something else, but in this figure, that's how they're drawn. They're like little lumps. And what inductors do is they store current, and then we have capacitors drawn like this. And these store charge slash they store voltage. And another thing to note is if you were to have uh, an inductor in with a voltage source, maybe we'll put a resistor up here or something like that. And if this, as this goes to infinity, or as this circuit sits for a very long time, the current through this whole circuit, say this is 5 volts, and this is 5 ohms. We know that voltage is equal to R times I. So voltage divided by resistance will give us current. So that'll have a current of 1 amp. And as this circuit sits for a while, what this inductor does is it resists the change in current. And if it sits for a long time, the current throughout the whole circuit will be the same. So it'll be 1 amp as it sits for a while. And if you were to have the same thing with a resistor and a capacitor, as this, whatever this voltage source and resistor end up being, as this voltage, or let's say as this current keeps going on for a while, as it goes to infinity or sits for a while, this charge, this 5 volts here, the whole entirety of it will be at this point, at the capacitor. It's going to store 5 volts of charge, or we'll just say it's just 5 volts, not 5 volts of charge. That's weird. But as it charges to 5 volts, nothing else will pass through the capacitor. It acts like a open circuit. And this inductor will act like a short circuit. Like shown. Because once a charge is stored, or, well, yeah, when the charge is stored fully on this capacitor, it won't store any more charge, because the polarities on both these sides are equal. So nothing is going to pass through. Okay. Now, we're going to go into how to combine resistors, which is how this homework is done here. So, capacitors combine the opposite of resistors. So say if you have two capacitors in series, or no, in parallel, point A to point B. They look like they're in series, but since these 2 points are different, it's in parallel. So this is going to be 1 microfarad. That's usually what they are. And this can be 1 microfarad. Now for capacitors in parallel, you just add them together. So this will become 2 microfarads. And for say if they were in series, you combine them like they're in parallel, like resistors. So we'll say they're 1 again, farad. You combine them as such, it can be 1 over 1 plus 1 over 1, which will be 2. And then you take that number and you put 1 divided by 2. You'll get 0.5. Or you could do it as this. You could do 1 plus 1 times both of them. And that'll also give you 1/2. Alright, and now we have inductors. Inductors combine exactly like resistors. So, for anyone that's been doing this course for a while should already know how to do this. If they're in parallel, well, you combine them like they're resistors in parallel. From A to B, we'll say it's 1. What is it in? Henries. 1 Henry. Henry. From point A to point B. If they're in parallel, you do the fraction of 1 over 1 plus, let's actually make it 2 so we can get a little bit harder. Do the 2 plus 1 over 2 is equal to 1. Grab the reciprocal. 1 over 1. Or you could do 1 raised to the negative 1. That also gets you 1. Or you could do 2 times 2 over 2 plus 2. And that'll get you 1. So if you combine them in parallel, they'll be 1 Henry. And if they're in series, you combine like they're in series. So 2 Henrys, 2 Henrys, that's the units for inductors. It'll be 4 Henrys. You just add them together. So, we're going to do the homework. We're going to start by doing this diagram here, and I'm going to draw it right now. Alright, now we have this circuit here drawn up. Okay, let's see how we can combine this. So, since inductors combine like resistors, we can see as we take the path from C to E, 2 resistors are in series. So, L6 plus L8. Alright, and that is in parallel from this C to E, and that also goes from C to E, is in parallel with L5. Okay. And now that we have one equivalent inductor from C to E, now if we travel the path from B to E this way, we'll have those in series. So this whole function plus L2. And then that's going to be in parallel with L4. Okay. And this is really just going to be your formula, right? You're going to combine these first. Whatever number you get there, you're gonna then do the formula for resistors in parallel with this one, for whatever number you get, and then you're gonna add that number to L2. And then after you get this final result, you're gonna do that number in parallel with L4. And that's gonna be the equivalent from points B to E, which is the first question on the homework. Then it wants it from A to D. Right, that's going to be part B. From A to D. So now that we know this number, we're going to call this a variable. We're going to call this Ln, right? That we just got. And Ln, we're going to draw an equivalent circuit really quick of what we just made. Okay, now that you've gotten this final result from your last question, right, you combined all these ones on the right from B to E, and now you have an equivalent inductor from B to point E. I want to get rid of those points, that doesn't confuse me. So, Ln is in parallel, oh no, my bad, is in series with L7. So as you travel from this point and go straight to D, Ln is in series with L7. And that's going to be in parallel with L3. See, as you go from this point, we'll call it B. As you go from B to D and B to D, they both have the same points, but they're not in series like these were. They're opposite from each other. I don't know. They're like that. It's over here and it's over here. So they're going to be in parallel. It's going to be in parallel with L3. That result. And then you're going to have one single inductor at the end, which is going to look something like this. After combining all those three, you're going to get something like this. And you just have two left. And as you travel from A to D, these two are clearly in series. So that means it's going to be in series with L1. And that will be your final answer, which is going to be 3.73, which is really close to the first one that I got. So yeah. Now we're going to move on to figure 2, which is capacitors. Okay. Now for capacitors, they're the opposite of how resistors combine. So let me draw this figure up really quick. Okay, now that we have this circuit, we're going to do about 2 to 3 different parts, just like it does in the question here. Once from 3 different parts. We're going to do from A to C over here. We're going to do from B to D over here. And then we're going to do a final one from A to B. Right. Okay, so let's start doing this. Let's do A to C first. So, from what I see, C1 and C3 are in series. C1. Let's say that the plus will be parallel, but the parallel... no, never mind, that's kind of silly. So since capacitors combine the opposite of resistors, I'm going to say that this is in parallel, even though they're in series, but they combine like they're in parallel. So we're keeping the same kind of notation, so that when we do the math or operation, it's going to be C1 plus C3 over C1 times C3. That's what's being operated when we do parallel for resistors. That's how you do them. And you're going to combine them like a resistor in parallel. So we're just going to use that for this case. So C1 parallel. No, they're in series, but you get what I'm saying. And then plus C4 because it's in parallel with this side over here. And for resistors and capacitors combine the opposite way that resistors do in series. They combine like resistors in parallel. No, they combine like resistors in series, my bad. Capacitors in parallel combine like resistors in series. That's what I meant to say. And then you're going to do this. And that should be the equivalent from A to C. Now let's do from B to D. These are in series and these are in series. So we're going to do C6 parallel, and they're in series. And then we can tell that from B to D that these two, whatever the resultants are going to be in series and parallel. I don't know why I keep messing that up. In parallel. They're going to be in parallel, so they're going to combine like they're in series. So we're going to do a plus to show that. C5, C7. When I'm using parallel, I actually mean plus for when I was using it up here. I'm just trying to show that you're doing the opposite operation from resistors when combining them. So you'll be doing the same operations that you're doing for parallel that you're doing up here. Then you're going to add those together. So we're going to call those new ones CF and CD. Those are going to be the final ones. And you're going to end up with a new circuit with capacitors. I'm going to draw that real quick. Okay, so we have our new circuit. This is going to be called C. We're going to call this CF. This is going to be called CD, and then this is going to be the same C2 up top. So how would you combine this? So we can say that you might go as to say that these are all in series, but they are not. So you have this point, and these share a common bottom. So think of it as something like this. They're in parallel. They're on the opposite sides. This is CF and CD. So they're in parallel in this case. Only because C2 is there. No. No, it's not because C2 there. So it's because it's in a loop. Right? The only time it's in series if it's a situation like this. As you're traveling through the same points from A to B, you don't have to go around like this from the same point to the other. Right? It's in the same line. This is in a different line. So if you go from, let's use C2 as a reference, and this is the bottom down here. You have to travel this way to C2 and this way to C2. So there's two different paths. And if they were in series, if you could get to this point down here without taking two, then they would be in series, but they're not. So it's going to be CF in parallel, but they combine like resistors in series. And then once you have that, you're just going to be left with a single capacitor. You're going to left with C2 like this. and CD, like so. Because once you, it's like folding a piece of paper with these two in parallel. They'll become one single line. And this will be the result. I'm just saying that they're in series now. And they're going to combine like resistors in parallel. And that is the equivalent from A to B. Okay. Now to figure 3. This one just wants you to solve it straight up, and I'm going to draw it really quick. Okay, now we're going to take a look at how current will act as we have these inductors here. So, we're given I3, I4, and I5. So I3, I4, and I5. So we're looking at this node here. So we know I3 is coming in, I4 is leaving down this way, and then we have I5 going to the right up top. So we have, and then we have I3 going down this way. So I'll try a little KCL for this. Right. So I3, no, my bad. I1 is coming in up top here. This is I1. So basically we're going to have something like this. Let me draw something better. So we have I1, I3, I4, and I5, and their directions are as shown. So let's try to KCL. Negative I1, since it's coming into this node up here, plus I3 since it's leaving, plus I4 since it's leaving, and plus I5 since it's leaving. Oops, not that big. Must be equal to 0. So to figure out the one we don't know, which is I1, right? Let's see. Extend. We must determine I1. So we know I3, I4, and I5. We can figure out I1. These are known, so we just plus the I1 over. So I3 plus I4 plus I5 is equal to I1. And there you go. And for our last one, we have capacitors, and we're going to look at how they react, or how they work with voltages. So currents with inductors, we're basically assuming that these are like in a steady state already. So like the current is constant at the time. So you can figure that out. But there's something called the transient state, and that's time when the current is varying for the inductor. But since there's no resistors, there's no dampening, which means there's nothing taking this current out of this ideal circuit. So it's going to keep the same value. So let's draw this capacitor really quick. Okay, so for this problem, we are given voltages. We're given V1, V3, V1, V3, V5, V6, and that's it. These are our knowns. So, from what I can see, here's V1, here's V3. We have two knowns and one unknown, V4, so we can do that to figure out V4. So we're going to do a KVL, a loop here. Plus to minus is going to be our positive, and negative to plus will be negative. So as we go in this loop, counterclockwise, we hit that plus to minus for V1, so it's going to be positive. Plus to minus for V3, so it's going to be positive. Minus the plus for V4, so it's going to be negative V4, is equal to 0. And then we can plus that V4 over, and then we're going to get this answer. And since we know V4, and we know V5, we know V4 now, and we know V6, we can figure out V2. We'll do a KVL going counterclockwise again. As we go through V4, that's going to be our plus to minus, positive. So V4 is going to be positive. Plus to minus for V6. So it's going to be positive. Plus to minus for V5. So positive V5. And minus to plus for V2. So it's going to be negative V2. Is equal to 0. Plus over the V2, and we have V4 plus V6 plus V5 is equal to V2. And that is your answer. So we solve for V4 in the first circuit on the left. Then we do the right. We plug in V4. We have three knowns, V4, V6, V5. So we can solve for our one unknown, V2, in the second circuit. And that's it. That is all the homework here, for the most part. So yeah. That concludes the inductor and capacitor sort of basics on how to combine them and kind of what they are. I'll go more into what they are in another video, like in a first and second order circuit. Goodbye.